So the third concept we want to look at is the idea of input substitution. There are different ways to think of input substitution. One of them is to look at what you can do in terms of trading off one input for another as you produce a fixed level of output, let's say why not, and from in basic production economics, the trade-off between inputs is something called the marginal rate of technical substitution. It tells you at what rate you can substitute one input for another, and that's what we have here. And of course, if you have other inputs, you need to use the partial derivative sign. It's also known as rate of technical substitution, marginal rate of technical substitution. They are the same name, same thing. So this is an interesting measure because it's based on the slope of the isoquant, and if the slope of the isoquant is flat or steep, it's telling you how easy or not easy it is to substitute one input for another. But when we are thinking about optimal input choice, it's not just the slope that we think about. We also are interested in the elasticity of substitution, and this concept is a measure of how curved the isoquant is. So it's the elasticity of input ratio with respect to the marginal rate of technical substitution. But the marginal rate of technical substitution, when you have optimized your input mix, is equal to the input price ratio. So in a way, the elasticity of substitution is measuring the responsiveness of the input ratio to the changes in the price ratio, and it's determined by how curved the isoquant is. And we will see what that means, but it's very easy to appreciate, because if I have an isoquant that's flatter, that flatter isoquant is going to tell me how my input mix changes when input prices change. And in this case, because it's flatter, there is a big change. But if that same isoquant had been curved, then you can imagine as you change your input price ratio, you don't travel far. That means the impact on the input mix is limited. So if the isoquant is more curved, there is less room for substitution, and that's captured by a small value for the elasticity of substitution. So the elasticity of substitution measures the curvature, the marginal rate of technical substitution measures the slope, and these are two very interesting concepts. Let's look at some more detail about the marginal rate of technical substitution. We said it's the rate of change in one input relative to another. It's a trade-off along an isoquant. You can simplify that, and using just basic calculations, you can show that the marginal rate of technical substitution is equal to the ratio of the marginal products. And in a two-factor world, if we are optimizing cost of producing a given level of output, which is described by this isoquant, then we are equating the price ratio or the slope of the isocost to the slope of the isoquant. The slope of the isoquant is that the price ratio, which is the slope of the isocost. Then if that's the optimal, another way to look at the optimal is to think in terms of the ratio of marginal product of an input to its price. And what this is telling us is, well, at the optimal, what we get in terms of output per input, we are producing the same input using this different same output using these different inputs. What we get in terms of output per dollar spent on an input should be equal across different inputs. So the same output for $1 spent. So if we have a case where the marginal product of input 1 per dollar spent on it is bigger than the marginal product of input 2 per dollar spent on it, then this is telling us, well, we are using too little of X1 and too much of X2, so we should be using more of X1 until its marginal product comes in balance with the marginal product of 2 when they are both divided by their respective input prices. While the marginal rate of technical substitution measures slope of isocant, as I said earlier, the elasticity of substitution measures the curvature, and if you want a formal definition, it's a proportionate change in the ratio of inputs relative to the percentage change in the marginal rate of technical substitution, which, as I said earlier, is also equal to the price ratio or the proportionate change in price ratio. So we are looking at this as the elasticity of substitution, and of course, since an elasticity measure, sometimes for derivations it's easier to think of the derivative of the log of the input ratio relative to the log of the marginal rate of technical substitution. And that's because when you have the derivative of a log with respect to the log of another quantity, then it's an elasticity. So it's useful to do exercises with and try to see if you can derive the different quantities we have discussed in this lecture. For example, if we have the production function, the square root one we saw earlier, where y is a function of x in such a way that output equals 4 times the square root of the input x. And if you have output prices and input prices being 3 and 1, then you can think of what the input demand is, what the output supply is, and what the optimal profit functions are. More than one way to do this, but the simplest one is to think of your problem as one of profit maximization. Think of profit being revenue less cost, and your revenue is P times Y, and your cost is, let's say, input price times input use. If I do that, I can substitute for Y, so I can have that. That's my profit now. But to optimize this, I need to work out what the first order conditions are. Now the first order condition says the derivative of my profit with respect to the choice variable I have, it's only x here, should be 0. But what is that derivative? That derivative is going to be, if I take the derivative of that formula, it's going to be 2 times P over square root of x minus W equals 0. And this is easy to solve because it's already telling me my x value is going to be 4 P square over W square. And if that's my optimal input, what is my optimal output then? Well, I plug in the optimal input into the production function, and that's going to give me 8 P over W. So my optimal output or supply curve is that one. That's my supply, and that's my input demand curve. So as you can expect, the input demand curve and the output supply curve have the expected properties. Input demand increase with output price and decrease with input price, and so on. And you can work out what the profit function is. I will leave that to you. If you go back to the production function we saw earlier and try to find the cost function, what would you find? Now we won't solve this here because it's slightly longer, but it's possible to derive, and it's done in Kohli et al. On page 22 you can find it. But you will be getting a cost function. You'll be getting a cost function, and that cost function should be cost being a function of input prices for the two and also the output level. And the problem is, what is that cost function? So if you solve it, you should be able to find a cost function. Of course, the cost function is derived from this output function, and it will be influenced by the parameters you have in here. but it's possible to do that and also calculate what's called the elasticity of cost. So this is again another concept of elasticity, and measures how responsive cost is to the scale of output. So it's related to the elasticity of scale, or the returns to scale measure we were describing earlier. And if you have increasing returns to scale, then the elasticity of cost should be less than 1, meaning your costs don't increase by the same proportion as your output, because you have increasing returns to scale. So that's easy to appreciate, but try to solve the cost optimization problem here. There is another example, but this example isn't analytical, it's empirical. There is data on wheat yield, and that's your Y value, and you have also inputs X1 and X2, and one of them is nitrogen, and you are asked to estimate a production function. No one has told you what it is, but I am suggesting that you try quadratic, but that quadratic has 2 inputs, not just 1, and you can work out what is the best form if you try different functional forms. But if you start with a quadratic, that might be flexible enough for you to get some reasonable results, but I will leave that to you. Then interpret the results, discuss if they are sensible, and using those results, which are your empirically estimated production function, then calculate the marginal product and try to see what it looks like for different observations in the data set. Write down your observations on that, and if you have data on the price of output, and if you assume that one of the inputs, which is X1, which is the growing season rain, is fixed at the average value for the sample, then basically what you are doing is, what was a 2-input production function, if I assume one of them is fixed at the mean value, which is rain, and this is nitrogen, then I am effectively turning the 2-factor production function into a 1-factor, and I can do what we have been doing so far, which is think in terms of nitrogen and output. If it's a quadratic function, it's going to be something like that. I can work out what the marginal products are and what the average products are, and I can work out what the optimal is very easily. Value marginal product being equal to marginal factor cost, but that's the price of the output times MP equals the input cost. You have the marginal product from your estimated function, the cost of input has been given, the price of the output is given, what's left is for you to figure out what that optimal is. So this is all doable, it's left to you as an exercise. So what else? Well, we have covered some basic concepts, but that's not all you can learn on this topic. So I encourage you to read Debertin. You can read many of these chapters very easily. You can also look at the chapter in Kohli. Kohli is a book on efficiency and productivity, so it's not standard production economics book, but it has got a chapter. You can also look at production functions chapter in Chambers. It's a famous book from 1988, widely known and a very good book. You can also look at Varian, which is an advanced micro economic theory book. There is a section on technology, and you can also find some of the derivations for the Cobb-Douglas in that book. But there are many other good production economics books that you can use. So make use of what's available to learn more and practice more, and don't forget to do the exercises. And we'll stop here.